If the universe stretches beyond what we can see, what could lie out there? Beyond the furthest galaxies and the limits of light since the Big Bang? The observable universe, about 93 billion light-years across, contains billions of galaxies. Yet beyond that is a vast hidden expanse we may never see. This other side challenges both physics and imagination, hinting at regions forever beyond our reach, where reality itself could be completely different. The universe we can observe is fundamentally limited by the speed of light and the finite age of the cosmos. Light travels at incredibly fast speed, yet it still takes time to traverse the vast distances of space. Since the Big Bang occurred roughly 13.8 billion years ago, the light from the most distant objects has only had so long to reach us. This defines the boundary of the observable universe. Anything beyond this distance exists in principle, but its light has not yet arrived at Earth. In other words, there may be regions of space that have existed for billions of years, but they remain invisible to us simply because photons from those regions have not had enough time to cross the expanding distances. However, this boundary is not a hard edge in space. Rather, it's a limit set by the finite speed of light combined with the expansion of the universe. Because space itself stretches over time, the observable limit is constantly increasing, but not fast enough to catch up with the farthest regions. Some areas are receding so quickly due to cosmic expansion that their light will never reach us, no matter how long we wait. This introduces a stark division between what we can observe and what we cannot, a distinction that emphasizes how our knowledge of the cosmos is inherently incomplete. Beyond the observable universe, vast stretches of space may host galaxies, stars, planets, or structures that are forever inaccessible. These unobservable regions could be similar to the parts we can see, or they might operate under entirely different cosmic conditions. We have no way to verify their contents because information from those regions cannot travel faster than light, and cosmic expansion itself may be accelerating those distances beyond reach. In essence, there is a vast, hidden universe lying beyond our perception, and while it may follow the same physical laws, it remains entirely speculative, waiting for theories, models, or phenomena that could hint at its nature. This observable versus unobservable distinction has profound implications for cosmology. It means that everything we know, from galaxy formation to the cosmic microwave background, is only a glimpse of the larger picture. The universe could be infinitely larger than the patch we see, yet we are confined to studying a finite, limited portion. Our understanding of the cosmos, no matter how advanced, is therefore bounded not by human intellect or technology alone, but by the fundamental constraints of space, time, and light itself. Beyond the limits of what we can observe lies the cosmic horizon, an invisible boundary marking the furthest reaches from which light has had time to reach us. This horizon is not an edge or wall in space. Rather, it represents a limit defined by the universe's age and the speed of light. Beyond this horizon, space continues, stretching into regions that, in principle, exist but remain forever beyond direct observation. The cosmic horizon reminds us that even though the universe may be vast, or even infinite, we are confined to a finite bubble of knowledge, a portion of reality illuminated by the light that has reached us over 13.8 billion years. Space beyond the cosmic horizon could be teeming with galaxies, clusters, and structures that mirror, diverge from, or surpass what we see. Because the universe is expanding, some of these regions are moving away faster than light can traverse the growing distances between us, meaning that the information they emit will never reach Earth. It's a humbling realization. Our view of reality is limited not by our tools, but by the fundamental structure of space-time itself. The cosmic horizon also implies that what lies beyond is unknowable in principle. We may develop models, run simulations, or predict patterns based on the observable universe, but the true contents of regions beyond our horizon could remain forever hidden, perhaps radically different from anything we can detect or imagine. This concept also ties closely to the nature of cosmic inflation, which suggests that in the first fractions of a second after the Big Bang, the universe expanded exponentially. This rapid inflation would have pushed enormous volumes of space far beyond what is now visible, creating regions that we may never see or interact with. The cosmic horizon, therefore, isn't merely a line marking what we can see. It is a gateway to an unreachable domain, a reminder that the universe is far larger, stranger, and more mysterious than our current observations can capture. Beyond the cosmic horizon, the universe may be teeming with galaxies far beyond our observational reach. While telescopes like Hubble and the James Webb Space Telescope have revealed billions of galaxies within our observable patch, there is no reason to assume these are all that exist. The unobservable universe could contain an unimaginably vast number of galaxies, each filled with billions or even trillions of stars, planetary systems, and potentially even forms of life. These galaxies might mirror our own, with familiar structures like spiral arms, elliptical cores, and clusters, or they could be completely alien, formed under slightly different conditions that give rise to shapes and behaviors unlike anything we have ever seen. The sheer scale is almost impossible to comprehend. If the universe is infinite, or even just vastly larger than the observable portion, the number of galaxies beyond our view could exceed anything we can imagine, stretching into regions that light has not yet reached and possibly never will. Each of these galaxies represents a cosmic ecosystem of matter, energy, and gravitational interactions that we can only speculate about. In some ways, the endlessness of galaxies serves as a humbling reminder of our limitations. Even with all our instruments and theories, we are only glimpsing a tiny fraction of the universe's total grandeur. This idea also intersects with our understanding of cosmic inflation. The early universe expanded so rapidly that entire regions of space were propelled beyond the reach of our observation. These areas may host galaxies formed under nearly identical physical laws, or perhaps under slightly altered conditions, giving rise to entirely new cosmic landscapes. The vastness of these endless galaxies also implies that every possible variation of galactic formation may occur somewhere, from the tiniest dwarf galaxies to enormous clusters spanning millions of light years. In essence, the universe may be not just large, but unimaginably full, a tapestry of countless galaxies woven beyond the limits of human perception. Cosmic inflation is one of the most profound ideas in modern cosmology, proposing that in the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion. During this incredibly brief instant, space itself stretched faster than the speed of light, growing from subatomic scales to macroscopic dimensions almost instantaneously. This rapid expansion explains several observed features of the universe, such as its large-scale uniformity, the smoothness of the cosmic microwave background, and the lack of magnetic monopoles or other exotic relics that theories predicted. But beyond solving these mysteries, cosmic inflation also has a staggering implication. It may have pushed enormous regions of space permanently beyond our observational reach. Because space expanded so quickly, patches of the universe that were once close together were separated by distances so vast that light from those regions could never catch up with us. These regions are effectively cut off from causal contact. They exist, but no signal, photon, or information from them will ever reach Earth. The consequences are mind-bending. Even if the universe itself is infinite, much of it remains forever hidden, a reality that inflation created in the very first moments of time. Some of these regions may contain entire galaxies, clusters, or cosmic structures that we can only theorize about, yet they are permanently beyond observation. Inflation also sets the stage for other mind-expanding concepts, such as the idea of bubble universes. If inflation occurred unevenly or continues in some regions, it could create separate pockets of space-time, each with potentially different physical constants and properties. This means that the universe we inhabit, the one governed by the laws of physics we know, could be just one bubble among countless others, all spawned from the same inflationary process. In short, cosmic inflation not only shaped the universe we can see, but may have permanently relegated vast portions of reality to the unobservable, leaving us with a patchwork of known and forever hidden cosmic domains. The universe is expanding, and this expansion is accelerating. One of the most profound consequences of this acceleration is the existence of regions that are, in principle, forever unreachable. To understand this, it is essential to distinguish between motion through space and the expansion of space itself. According to Einstein's theory of relativity, no object can move through space faster than light. However, space itself is not bound by this speed limit. During the expansion of the universe, the very fabric of space stretches, carrying galaxies with it. In distant regions, this expansion can outpace the speed of light, meaning that two galaxies might be moving away from each other faster than photons could bridge the distance. From our perspective, these regions are effectively cut off. Light emitted from them now will never arrive, and no signal or probe could ever reach them. This idea introduces a staggering limitation on our ability to explore the cosmos. Even though we can peer billions of light years into space and study galaxies as they were billions of years ago, there are volumes of the universe whose light will never reach us. These unreachable regions exist because the expansion of space increases the proper distance between us and them faster than light can traverse that distance. As a result, some parts of the universe are permanently beyond observational contact. They are not destroyed, invisible in some conventional sense, or extinguished. They are simply moving away from us at a rate that makes any interaction physically impossible. This effect becomes increasingly significant as we consider the universe at ever larger scales, revealing a reality where the cosmos is not only vast, but fundamentally partitioned into accessible and inaccessible domains. The consequences of unreachable regions are profound for cosmology and our understanding of reality. For instance, we often assume that the universe is homogeneous and isotropic, meaning it is roughly the same in all directions and locations. Yet, because some areas are forever beyond our reach, we can never verify this assumption across the entirety of space. What lies in these inaccessible regions may mirror what we see in our observable patch, or it could diverge dramatically. There could be clusters of galaxies, voids larger than anything we know, or even domains where the laws of physics manifest differently if conditions vary slightly on scales beyond our observational horizon. The unreachable regions of the universe are, therefore, a reminder that our knowledge, while vast, is inherently limited, and that what we can study is only a fraction of the cosmos. To quantify this, consider the current observable universe, which spans roughly 93 billion light-years in diameter. Beyond that lies the unobservable region, and as space continues to expand, more areas that were once observable may drift beyond our cosmic event horizon. This expansion is not hypothetical. Observations of distant supernovae, the cosmic microwave background, and the large-scale distribution of galaxies indicate that the universe's expansion is accelerating, likely due to dark energy. Dark energy acts as a repulsive force at cosmological scales, increasing the rate at which space stretches and thus pushing more regions beyond reach. Over billions or even trillions of years, distant galaxies that are visible today will redshift into invisibility, fading from our sky as if swallowed by the expanding void. In this sense, the universe is becoming progressively more isolated, with local structures like our Milky Way and its neighboring galaxies remaining accessible, while the rest drifts away into permanent darkness. The existence of unreachable regions also shapes our theoretical understanding of the universe. Cosmologists must model not just what we see, but what we can never see, inferring properties of the cosmos beyond observational limits. These models rely on assumptions about the uniformity of matter, the behavior of dark energy, and the initial conditions set by the Big Bang and cosmic inflation. Yet, the very fact that regions are unreachable introduces a layer of uncertainty that may never be resolved. We can extrapolate based on what is observable, but these extrapolations are just that, educated predictions. There may be entire structures, phenomena, or physical constants that differ in unreachable regions, forever beyond our capacity to detect or measure. This raises philosophical questions about the nature of reality. Can we claim comprehensive knowledge of the universe if portions of it are, in principle, inaccessible? Unreachable regions challenge the assumption that the universe is fully knowable and force us to confront limits inherent in the very structure of space-time. Furthermore, unreachable regions emphasize the dynamic nature of space itself. While light and matter obey physical laws locally, the metric expansion of space operates on a global scale. This means that what we perceive as the edge of our observable universe is not a true edge, but a moving boundary defined by the interplay of cosmic expansion and light travel. Galaxies that appear near this edge are not moving through space faster than light. They are carried away by the stretching of space. This distinction is crucial, as it reconciles the seemingly paradoxical idea that objects can recede from us faster than light without violating relativity. From a practical standpoint, it also means that the universe contains intrinsic regions that will remain forever beyond causal contact, creating a permanent partition between the observable and the eternally unreachable. The concept of unreachable regions also has implications for the ultimate fate of the universe. If cosmic expansion continues indefinitely, driven by dark energy or some other mechanism, an ever-increasing portion of the universe will slip beyond our reach. Over unimaginably long timescales, this could isolate galaxies, clusters, and superclusters, leaving each gravitationally bound system in isolation, separated by expanding voids too vast for light to cross. Future astronomers, even if vastly more advanced than we are today, might see only a tiny portion of the cosmos, losing access to evidence of the universe's vast past and large-scale structure. In a sense, the universe is already partitioned into an observable now and a growing set of unreachable regions, each evolving independently, drifting into darkness beyond our horizon. The existence of these unreachable regions reinforces the humility with which we must approach cosmology. While our telescopes, satellites, and instruments provide staggering insights into the universe, they cannot capture the totality of reality. Regions beyond our reach might hold galaxies, cosmic phenomena, or physical behaviors entirely alien to our experience. The universe, in this sense, is both known and unknowable. We study its observable fraction in immense detail, yet we must accept that other portions will remain eternally inaccessible, never sending us light, information, or clues about their existence. It is a humbling reminder that even in an era of extraordinary scientific advancement, some aspects of the cosmos remain permanently hidden, a frontier defined not by imagination or technology, but by the very structure of space-time and the relentless expansion of the universe. The concept of an infinite universe pushes the mind to the very limits of comprehension. Unlike the observable universe, which is constrained by the finite speed of light and the age of the cosmos, the infinite universe theory suggests that space itself may have no boundary or edge, extending endlessly in every direction. In this framework, the regions we can see are just a tiny fraction of an unfathomably larger cosmos. And beyond the cosmic horizon, there could be an infinite expanse filled with matter, energy, and structures much like, or perhaps unlike, those we observe. The infinite universe challenges our intuitive understanding of scale. If the cosmos is indeed infinite, then every possible arrangement of matter may occur somewhere, from exact copies of galaxies to star systems that mirror our own, and even improbable configurations that defy our expectations entirely. The notion of an infinite universe has its roots in both observational evidence and theoretical models. Observations suggest that on large scales, the universe appears homogeneous and isotropic, meaning it looks roughly the same in every direction. This uniformity supports the idea that there's no preferred center or edge, implying the universe could continue indefinitely. Inflationary theory also complements this concept. During the brief but dramatic inflationary period following the Big Bang, space expanded exponentially, potentially producing regions that extend far beyond what we can observe. If inflation is correct, then it's possible that the universe's expanse continues forever, growing into a boundless sea of matter and energy beyond even the most powerful telescopes. An infinite universe also has staggering implications for probability and cosmology. In a cosmos without end, every combination of particles could theoretically occur somewhere. This includes the replication of entire galaxies, solar systems, and possibly even arrangements of life. While this may seem like science fiction, it is a natural outcome of infinity. Given unlimited space, statistical inevitability ensures that patterns and structures can repeat, potentially in ways indistinguishable from our own surroundings. The infinite universe, therefore, introduces a level of cosmic redundancy and variation that is both mind-boggling and profoundly humbling. It forces us to confront the idea that our universe, with all its familiar stars, planets, and laws, may be just one tiny patch in an eternal expanse. Yet, the infinite universe is not without conceptual challenges. Infinity is a mathematical abstraction that is difficult to reconcile with physical reality. Philosophers and physicists debate whether the universe can truly be infinite, or if what appears infinite is just unimaginably large. An infinite universe may also confront the limits of human comprehension. Our brains and intuitions evolved to navigate finite environments, so imagining a cosmos without bounds requires a leap into abstract thought that strains our capacity for understanding. Regardless of whether the universe is finite or infinite, the theory fundamentally alters our perspective on existence, highlighting the possibility that what we see is only a tiny fragment of an unending cosmic panorama. In addition, an infinite universe challenges the very concept of location. In a finite universe, it makes sense to talk about here versus there, edges and boundaries. But in an infinite universe, every direction you look is just a continuation of more space, more galaxies, more cosmic structures. There is no center, no ultimate edge, and no final frontier, only a continuous expanse extending indefinitely. This notion also affects cosmological measurements. While we can measure distances, densities, and structures within the observable universe, Any attempt to extrapolate these properties to infinity remains speculative, relying on assumptions that the laws of physics and patterns we observe locally persist on a scale we can never fully confirm. Furthermore, the infinite universe concept intersects with other extraordinary theories, such as the multiverse and quantum cosmology. If space is truly unbounded, it raises the possibility that regions with different physical constants, different outcomes of quantum events, or even alternate versions of fundamental particles might exist somewhere far beyond our reach. In this sense, the infinite universe could contain not only endless repetitions of familiar structures, but also entirely novel realms, each with its own unique arrangement of matter, energy, and laws. The combination of unbounded space and limitless variation challenges us to expand our understanding of reality far beyond the human scale. The philosophical implications are equally profound. If the universe has no end, then questions about a boundary or other side lose their conventional meaning. There may be no edge to reach, no ultimate wall of space, and no final destination, only infinite extension. This forces a re-evaluation of human significance and the nature of existence itself. In an infinite universe, our place is simultaneously insignificant in scale, yet extraordinarily unique in context. For we can observe, measure, and contemplate a patch of the cosmos that is comprehensible to us, even if it is but a minute fraction of the whole. The infinite universe thus becomes a realm of paradox, limitless, yet containing the finite experiences and knowledge of conscious beings capable of reflection. While the idea of an infinite universe stretches the imagination, cosmologists also consider a profoundly different possibility, that space might be finite yet unbounded. This concept arises from the idea of curved space, which challenges the intuitive notion that a finite object must have an edge. In curved space, moving in a straight line in any direction could eventually bring you back to your starting point, much like traveling on the surface of a sphere. From a local perspective, space appears flat, but on cosmic scales, it could bend, creating a finite yet boundless geometry. If the universe behaves this way, it may have a measurable volume, yet no true boundary or edge exists. There is no outside to reach, only an endless loop of space. The geometry of space is determined by its overall mass-energy content and the cosmological constant. According to Einstein's general relativity, mass and energy curve space-time, and this curvature can extend across the universe. Observations of the cosmic microwave background and large-scale galaxy distributions suggest that, on the largest scales we can measure, space is nearly flat. Yet a slight curvature, positive or negative, could still exist beyond our observational horizon. If space has positive curvature, it behaves analogously to the surface of a 3D sphere embedded in 4 dimensions. Traveling far enough in one direction could theoretically return you to your point of origin, just as circumnavigating the Earth eventually brings you back to your starting location. This idea allows the universe to be finite in volume while evading any notion of an edge. Curved space introduces fascinating implications for cosmology and perception. In a finite but unbounded universe, light, traveling across cosmic distances, could eventually loop back, creating multiple images of the same galaxy or cluster in different parts of the sky. This phenomenon, sometimes referred to as topological lensing, is a potential observational signature of a curved universe. Detecting such patterns would provide profound insight into the universe's true geometry, revealing whether our cosmos is not infinite, but rather a vast, looping structure beyond our immediate perception. However, no definitive evidence of repeated images has been observed yet, leaving the curvature question open and tantalizingly mysterious. Moreover, curved space reconciles the idea of a finite universe with the absence of boundaries. Unlike an infinite universe, where every possible arrangement of matter must occur somewhere, a finite unbounded universe has a limited volume. Yet within that volume, there is no point where the universe ends. The lack of an edge does not imply infinity. Instead, it emphasizes that our human intuition about boundaries and edges does not necessarily apply on cosmic scales. In this sense, curved space challenges fundamental assumptions about direction, distance, and the meaning of a boundary, forcing us to rethink the nature of what we perceive as outside or beyond. This concept also intersects with other cosmic mysteries. If space is curved and finite, it may influence the ultimate fate of the universe. Positive curvature could eventually slow cosmic expansion, potentially leading to a collapse in a big crunch. Negative curvature, conversely, would cause indefinite expansion. Observing the exact curvature is therefore not just a geometric question, but one that shapes cosmological predictions about the universe's evolution. Even a slight curvature beyond our observational horizon could result in profound effects on large-scale cosmic structure over billions or trillions of years. Curved space also has implications for the philosophical question of what lies beyond the universe. If the cosmos loops back on itself, the very idea of an other side loses meaning. There is no exterior region, no void to step into, and no boundary to cross. The universe becomes a self-contained whole, finite in extent, but infinite in navigational possibility. Traveling straight in any direction eventually returns you home, illustrating that finiteness and boundlessness are not mutually exclusive. This duality forces a reconsideration of concepts like edges, limits, and external space, suggesting that the universe could be a complete structure with no outside, yet still vast enough to appear limitless from within. Furthermore, a finite yet unbounded universe has profound implications for cosmological models and calculations. Determining the density of matter and energy, predicting the behavior of cosmic structures, and modeling the evolution of the cosmos all rely on assumptions about geometry. Curvature affects gravitational dynamics, light paths, and the growth of structures over cosmic time. Even subtle curvature beyond our observational reach could alter predictions about galaxy formation, dark matter distribution, and cosmic expansion, highlighting that the universe's shape is not a mere abstraction, but a factor with tangible consequences for everything we see and measure. The implications of a multiverse are staggering, extending far beyond our observable universe and profoundly challenging our conception of reality. If other universes exist, each could possess completely different physical laws, constants, and dimensional structures. One universe might have a stronger or weaker gravitational constant, preventing stars from forming, while another could have different fundamental particle interactions, leading to exotic forms of matter that are completely alien to our understanding. Some universes might support complex chemistry and life, while others may be sterile voids with no structures beyond elementary particles. The sheer scale and variety implied by a multiverse suggests that our universe, so meticulously arranged to allow galaxies, stars, planets, and conscious life, might be just one of countless possibilities in an infinite cosmic landscape. This perspective challenges the notion that our universe is special or unique. Rather, it could be one small instance among an almost unimaginable number of realities, each unfolding according to its own initial conditions and physical laws. From a scientific standpoint, the multiverse arises most naturally from the combination of eternal inflation and string theory's landscape of possible solutions. In eternal inflation, some regions of space stop inflating and form distinct universes, while other regions continue to inflate exponentially. Each bubble universe that emerges in this process can have its own set of constants, forces, and particle properties, essentially functioning as a self-contained cosmos with its own timeline and evolution. Meanwhile, string theory predicts a vast number of stable vacuum states, each corresponding to a different configuration of extra dimensions and physical laws. Taken together, these theories suggest a staggering multitude of possible universes, forming a complex cosmic mosaic where the diversity of reality extends far beyond our observable domain. The multiverse, in this sense, is not a wild speculation, but a natural outcome of theoretical frameworks that successfully describe the physics of our universe. Quantum mechanics further expands the multiverse picture through the many worlds interpretation, which posits that every quantum event with multiple possible outcomes generates a branching of reality. In this framework, every decision, every particle interaction, every quantum fluctuation results in a separate, parallel branch of the universe. These branches are equally real, yet they exist in separate dimensions of reality, forming an infinitely branching structure of parallel worlds. Within this quantum multiverse, every conceivable version of events is realized somewhere. A universe where life never emerged on Earth, a universe where our Milky Way never formed, or a universe where completely different physical principles apply, all exist as part of this vast, branching ensemble. This concept implies that reality is far more expansive and intricate than anything we can perceive or imagine, encompassing not just what exists spatially beyond our cosmic horizon, but also the full spectrum of possibilities at every quantum level. The multiverse hypothesis also provides a potential solution to the fine-tuning problem of our universe. Observations indicate that the fundamental constants of physics, such as the strength of gravity, the masses of elementary particles, and the cosmological constant, lie within narrow ranges that permit the formation of complex structures and the emergence of life. The probability of these constants having exactly the values we observe seems extraordinarily small, raising the question of why the universe appears so finely tuned. If the multiverse exists, the answer may be statistical rather than exceptional. With countless universes each having different constants, it is inevitable that some fraction will have the conditions necessary for life. We find ourselves in such a universe not because it is unique or miraculous, but because only universes with the right conditions can support observers capable of asking these questions. This perspective, sometimes framed as the anthropic principle, shifts our understanding from uniqueness to inevitability, placing our universe within a broader, diverse ensemble of realities. Despite its explanatory power, the multiverse presents profound challenges for observation and verification. By definition, the other universes are causally disconnected from ours. No light, radiation, or matter can cross the boundaries created by rapid inflation or the separation of space-time regions. Some theorists suggest that subtle imprints of collisions between bubble universes might be detectable in the cosmic microwave background, such as slight anomalies or patterns that hint at interactions in the early universe. Others propose that the statistical distribution of physical constants in our universe could indirectly support the multiverse, though such evidence is circumstantial. At present, direct observation remains impossible, which has led to intense debate about whether the multiverse belongs in the realm of science or metaphysics. Nevertheless, many physicists argue that if a theory predicts a multiverse as a natural consequence, and if that theory is otherwise consistent with observations in our own universe, the existence of other universes should be taken seriously as a plausible component of reality. Philosophically, the multiverse reshapes our understanding of reality, existence, and identity. In a landscape of countless universes, the notions of here and now take on new meaning. Our universe, our planet, and even our individual lives are but one manifestation among infinite possibilities. Questions about purpose, uniqueness, and cosmic significance are reframed. In a multiverse, the conditions that allow life or conscious observation are not miraculous but expected, given the immense variety of cosmic configurations. This perspective can be simultaneously humbling and liberating, offering a vision of reality in which every possible scenario is realized somewhere. Yet our own experience remains deeply meaningful because it occurs within the specific parameters of our universe. The multiverse also introduces mind-bending possibilities for the ultimate nature of reality. If universes can exist with different laws of physics, then concepts we take as universal, gravity, quantum mechanics, the speed of light, may not apply elsewhere. The very notion of time, space, or causality could differ radically, creating realms of existence beyond the grasp of human intuition. In some hypothetical universes, stars may never form, space may have more than 3 dimensions, or matter may behave according to entirely alien principles. The sheer scale of potential diversity challenges the limits of imagination. We can describe universes using mathematics, but truly visualizing the variations is likely impossible. This reinforces the idea that reality may be far larger, stranger, and more diverse than our observational universe alone would suggest. The multiverse connects seamlessly to the broader themes of cosmic mystery explored throughout the discussion. Just as unreachable regions and the cosmic horizon define limits to what we can observe, the multiverse stretches those limits even further, proposing a reality in which the other side is not merely more space, but entirely different realms of existence. It blurs the line between the observable and the theoretical, the known and the unknowable. The multiverse expands the frontier of inquiry beyond astronomy and cosmology, inviting profound questions about the nature of reality, the role of observers, and the ultimate scope of existence. In contemplating the multiverse, we are reminded that our universe, with all its stars, galaxies, and life, may be just one thread in a tapestry of infinite possibilities, an island of order and structure in a sea of boundless, mysterious creation. Bubble universes, sometimes called pocket universes, are a striking extension of the multiverse concept, emerging naturally from the physics of cosmic inflation. During the first fractions of a second after the Big Bang, space expanded exponentially in a process driven by a high-energy vacuum state. Inflationary theory suggests that this expansion was not uniform. Some regions stopped inflating and settled into lower energy states, forming distinct domains of space-time, what we call bubble universes. Meanwhile, inflation continued in other regions, creating new bubbles. Each bubble is essentially a self-contained universe, with its own initial conditions, structure, and possibly even laws of physics. Our universe could be just one bubble among an unfathomably vast number, each potentially differing in its fundamental constants, particle content, or spatial dimensions. The formation of bubble universes relies on the nature of the inflationary field, often described as a scalar field permeating space. This field can be in a high-energy, false vacuum state, which drives rapid expansion. Occasionally, regions decay into a lower-energy, true vacuum state, ending inflation locally and creating a bubble. Once formed, the bubble evolves independently, cooling, forming matter, and potentially generating galaxies, stars, and planets, much like our own observable universe. Meanwhile, surrounding regions may continue inflating indefinitely, giving rise to yet more bubbles. This process, sometimes called eternal inflation, suggests a never-ending creation of universes, each a bubble in an ever-expanding cosmic foam. What is particularly fascinating about bubble universes is that each one could have its own distinct laws of physics. While our universe obeys the familiar rules of electromagnetism, gravity, and quantum mechanics, another bubble might have slightly different fundamental constants. Gravity could be stronger or weaker, the electromagnetic force could behave differently, or the ratio of protons to electrons could vary. Some bubbles might permit the formation of complex structures and life, while others remain barren or consist entirely of exotic matter. The diversity of bubble universes illustrates a profound truth. The cosmos we inhabit is not necessarily normal or inevitable. It is simply one outcome among an uncountable array of possibilities, each realized in its own domain. Bubble universes also challenge our understanding of causality and connectivity. Once formed, each bubble is generally isolated from others by rapidly inflating space, which stretches distances beyond the reach of light or other signals. This means that while multiple bubbles may exist simultaneously, they are effectively causally disconnected. No observer in one bubble can directly communicate with or observe another. From a practical standpoint, this isolation makes bubble universes fundamentally unreachable, yet their existence is implied by the physics of inflation and the mathematical consistency of cosmological models. In essence, the universe may be far larger and more diverse than we can ever experience directly, with each bubble representing a unique cosmic laboratory. The concept of bubble universes also raises deep philosophical and scientific questions. If there are countless bubbles, each with different physical laws, then our universe may not be unique in its ability to support life. This perspective provides a natural explanation for the so-called fine-tuning problem, which asks why our universe has the precise conditions necessary for stars, planets, and consciousness to emerge. In a multiverse of bubble universes, the existence of a life-permitting cosmos is not miraculous. It is statistically inevitable. Observers like us will naturally find themselves in bubbles where conditions allow complexity and consciousness to arise, while countless other bubbles remain sterile or radically different. Bubble universes also extend the notion of cosmic diversity to extreme levels. In addition to variations in physical constants, some theories suggest that bubble universes could differ in dimensionality, with more or fewer spatial dimensions than our familiar three. Others might experience radically different evolutionary timelines, expansion rates, or energy distributions. In some hypothetical scenarios, the universe could emerge in a bubble with chaotic or unpredictable properties, giving rise to structures and dynamics that would seem almost magical from our perspective. The range of possibilities is so vast that it is difficult for human imagination to encompass it fully, illustrating just how limited our experience of reality truly is. Furthermore, bubble universes intersect with the larger multiverse concept by suggesting that the cosmos is not a singular unified entity, but rather a dynamic, ongoing process of universe creation. Inflation continuously generates new bubbles, and these bubbles may spawn new regions of space-time, leading to an ever-expanding, self-replicating cosmic structure. The entirety of this structure, the inflationary multiverse, could be infinite, containing universes with every conceivable variation of matter, energy, and physical law. Our observable universe, then, is merely one small, familiar bubble embedded in a vast, exotic, and largely inaccessible cosmic foam. The study of bubble universes also drives profound implications for the ultimate limits of human knowledge. Since these universes are separated from ours by exponentially expanding space, we can never observe or interact with them directly. Their existence must be inferred from theoretical models and the internal consistency of physical laws rather than empirical measurement. This introduces a layer of epistemic humility. Even as we probe the deepest aspects of the cosmos, vast domains of reality may remain forever beyond our reach, governed by the same physical processes that created our universe, yet unfolding in entirely inaccessible contexts. Bubble universes also offer a potential framework for understanding the origin and evolution of our own cosmos. By studying the mechanics of inflation, the behavior of scalar fields, and the energy landscape that drives universe formation, cosmologists can gain insights into why our universe has its particular properties, even if other bubbles differ dramatically. In this sense, bubble universes are both explanatory and humbling. They provide a mechanism for the diversity of cosmic outcomes while highlighting that our universe is just one of many possible manifestations of fundamental physical principles. Beyond the cosmic bubble we inhabit, the very foundations of reality might be radically different. While the laws of physics, as we understand them, gravity, electromagnetism, quantum mechanics, and the strong and weak nuclear forces, govern every process in our universe, there is no guarantee that these rules apply universally. The observable universe, limited by the cosmic horizon, offers only a glimpse into a tiny fraction of all that exists. Beyond that horizon, regions could exist where the constants of nature differ, particles behave differently, or entirely new forces dominate, creating realms of reality that defy our intuitions and experiments. These possibilities are not mere flights of fancy, but arise naturally from theoretical frameworks like the multiverse, cosmic inflation, and string theory, which predict variations in fundamental parameters across different regions of the broader cosmos. For instance, imagine a region where the fine structure constant, the number governing the strength of electromagnetic interactions, varies slightly. Such a change could dramatically alter the behavior of atoms, chemistry, and the formation of molecules. Stars might burn at radically different rates, planets may not form, or the concept of stable matter could be non-existent. In some regions, gravity might be weaker, preventing galaxies or stars from coalescing, while in others, it could be stronger, collapsing matter into dense, unfamiliar structures. There could even be realms where entirely new forces emerge, ones that have no analogue in our physics, producing phenomena that seem almost magical from our perspective. The diversity of possibilities is staggering. Beyond our cosmic horizon, the fabric of reality could host a bewildering array of physical laws, some permitting complexity and life, others a barren, alien vacuum. The notion that physical laws could vary across space is closely linked to string theory and the landscape of vacua. In string theory, the geometry and configuration of extra dimensions determine the behavior of fundamental forces and particles. Different configurations, or vacua, can result in universes with radically different physics. Our universe, with its particular constants and interactions, may be just one realization among an enormous ensemble, each corresponding to a distinct combination of vacuum states. Some of these alternate configurations might allow for familiar structures, while others could produce entirely alien environments, potentially with more or fewer spatial dimensions, exotic forms of matter, or unfamiliar symmetries. The implication is profound. The rules we take for granted may be local rather than universal, governing only the particular patch of the cosmos we inhabit. This perspective also opens the door to extreme cosmological diversity. Beyond our observable universe, there might exist regions with exotic forms of matter, like strange quark matter or hypothetical particles not found here. In some areas, the speed of light, the strength of gravity, or the ratios of fundamental particles could differ, resulting in physical processes that defy our comprehension. Perhaps in certain domains, atoms cannot form stable structures, or time behaves differently, flowing irregularly or in multiple directions. The universe as we know it could be just one particular manifestation of a far broader spectrum of physical realities. By extending our imagination into these possibilities, we begin to appreciate the limits of empirical knowledge. We can only study what is accessible, while the majority of the cosmos may be governed by physics that remains forever beyond our ability to probe. The consequences of variable physics also ripple into cosmological structure and evolution. In some regions, stars might never ignite, galaxies might fail to form, and chemistry might not allow for complex molecules. In others, unusual forces might give rise to structures completely alien to our experience, forming vast networks of matter or energy that follow rules entirely different from gravity or electromagnetism. The diversity of possibilities implies that our observable universe, despite its vastness, may be a tiny and highly constrained example of what is possible. From this perspective, the familiar cosmos of stars, planets, and galaxies is not necessarily a blueprint for the broader universe, but rather a lucky configuration amid potentially infinite variations. Speculating on other laws of physics also raises profound philosophical questions. If reality operates differently beyond our observable horizon, then what we perceive as universal truths may be parochial, valid only within the constraints of our local cosmic environment. The constants and laws we measure, the behavior of matter and energy, and even the principles underlying cause and effect could be contingent rather than absolute. This challenges the notion that physics provides a universal description of reality. Instead, it may describe only a subset of existence, an island of order in an ocean of alternative possibilities. Our understanding of laws might therefore be as limited as a creature on a flat plane attempting to comprehend a higher dimensional universe. The potential for radically different physics also intersects with other cosmological ideas, such as bubble universes and the multiverse. Each bubble could be governed by its own unique laws, creating a patchwork of realities across the larger inflating space. Some bubbles might resemble our universe closely, allowing familiar structures to emerge, while others could be entirely alien, with no matter, no stable atoms, or no recognizable form of energy. These differences illustrate the staggering scope of what beyond the universe might entail. It is not merely more galaxies or empty space, but potentially entirely new frameworks of existence. Within this framework, our universe is a privileged domain where the laws allow for complexity and life, but it is far from guaranteed that such conditions prevail elsewhere. The notion that physics itself could vary also reshapes our understanding of the other side of the universe. Rather than being a simple extension of what we see, these regions could host realities so alien that the concept of space, time, or matter may lose its meaning. Observers within these regions, if any could exist, would inhabit worlds governed by entirely different principles, perceiving reality in ways utterly foreign to us. This reinforces the limits of human knowledge. Our measurements, experiments, and theories are constrained to our universe and its physics, while the broader cosmos may be a theatre of unimaginable diversity, largely hidden from us. In essence, the idea of other laws of physics stretches the concept of the universe from a single, knowable system into an almost infinite spectrum of possibilities. It reminds us that our understanding of reality, as vast and profound as it may be, remains local and provisional. Beyond the horizon lies not just more space or more matter, but potentially entirely new frameworks of existence. where the rules we take for granted are replaced with conditions that challenge the very foundations of comprehension. The observable universe, with its predictable laws, becomes just a sliver of what may exist in the grander cosmos, a reminder that the ultimate reality may be far stranger and more diverse than we could ever hope to measure or imagine. Beyond the familiar 3 dimensions of space and 1 of time, the universe may extend into realms of higher dimensions, a concept that challenges our most basic intuitions about reality. Higher dimensional theories arise naturally from the intersection of general relativity, string theory, and other attempts to unify the fundamental forces. In such models, our observable universe could be just a 4-dimensional slice embedded within a much larger multidimensional reality. These additional dimensions may be compactified, curled up at scales too small to detect, or they might extend infinitely, invisible to us, because our senses and instruments are constrained to perceive only the familiar dimensions of length, width, height, and time. The notion that there could be realms beyond our perception introduces a radical expansion of the concept of space, suggesting that the universe we inhabit is merely a local projection of a far more intricate structure. String theory, one of the leading frameworks incorporating higher dimensions, posits that particles are not point-like, but rather tiny vibrating strings whose modes of vibration determine particle properties. To be mathematically consistent, string theory requires extra spatial dimensions, up to 10 or 11 in some versions. These hidden dimensions could govern the strengths of forces, the masses of particles, and the very laws of physics we observe. If our universe is embedded in a higher dimensional space, it becomes plausible that the limitations and constants we take for granted are consequences of how our 4-dimensional brain exists within this larger structure. Some forces, such as gravity, may even partially propagate into these higher dimensions, which could help explain why gravity is so weak compared to other forces. In essence, higher dimensions offer a mechanism by which the physical properties of our universe arise from geometry and topology in a space far larger than what we can observe. The idea of higher dimensions also opens the door to extraordinary possibilities about what lies beyond our observable cosmos. Entire regions of space may exist in directions and dimensions that are orthogonal to the ones we can perceive. In these hidden realms, matter and energy might behave differently, structures might form according to unknown principles, and the passage of time could vary from our own experience. These dimensions could host universes or sheets of reality parallel to ours, potentially interacting weakly or occasionally strongly with our own universe. The notion that reality has layers beyond perception challenges the idea of a single, all-encompassing universe and reframes the concept of the other side as potentially multidimensional, not just spatially distant. Higher dimensional spaces also provide a theoretical framework for brain cosmology, where our universe is conceptualized as a 4-dimensional brain, floating in a higher dimensional bulk. In this model, other brains could exist alongside ours, separated by extra-dimensional distances. Interactions between brains might manifest in our universe as gravitational anomalies, high-energy cosmic events, or other subtle effects. Some speculative ideas suggest that the Big Bang itself could have been the result of a collision between brains, giving rise to the universe we observe today. If true, our universe is not a singular entity, but one of potentially countless brains, each embedded in a richer, multidimensional reality. These interactions, while currently beyond experimental reach, provide a powerful illustration of how higher dimensions could influence our observable cosmos in ways both subtle and profound. The existence of higher dimensions also has implications for the structure and topology of the universe. If space extends into additional dimensions, the cosmic geometry may be far more complex than our intuition suggests. Space could loop, fold, or intersect in higher dimensional patterns, creating pathways and regions entirely inaccessible from our familiar three-dimensional perspective. Light, matter, and energy could propagate through these dimensions in ways that are invisible to us, producing indirect effects such as gravitational anomalies or phenomena like dark matter and dark energy, which remain mysterious in conventional four-dimensional models. Higher dimensions provide a framework in which these enigmatic observations could be natural consequences of a richer underlying geometry. Philosophically, higher dimensions challenge our perception of reality itself. Humans evolved to navigate a three-dimensional environment, and our brains interpret space, motion, and causality through this limited lens. Considering higher dimensions forces a cognitive leap. What seems impossible or paradoxical in three dimensions, such as objects passing through each other, spaces folding back on themselves, or universes interacting without visible connection, could be ordinary in higher dimensional contexts. The very idea of an other side may therefore be misleading. Beyond our observable universe, reality may extend in directions that we cannot intuitively grasp, where conventional notions of distance, separation, and boundary lose meaning. Higher dimensional theories also integrate elegantly with other cosmological ideas, such as the multiverse and bubble universes. If multiple universes exist, they could occupy different brains in higher dimensional space, isolated from one another, yet possibly interacting through gravity or other forces propagating in extra dimensions. This adds a layer of unity to seemingly disparate concepts. Unreachable regions, bubble universes, and alternate laws of physics might all be manifestations of higher dimensional structure. The universe we perceive is merely the local, observable projection of a vast, multi-dimensional reality whose full scope may be forever beyond direct observation. The potential consequences of higher dimensions extend even to the ultimate fate of the universe. The dynamics of extra dimensions could influence cosmic expansion, the distribution of matter, and the evolution of large-scale structures. They might allow phenomena that appear impossible in four-dimensional physics, such as shortcuts through space-time, akin to wormholes, or interactions between distant universes. In this sense, higher dimensions are not just mathematical curiosities. They may fundamentally shape the behavior, evolution, and scope of reality itself. Brain cosmology builds directly on the concept of higher dimensions, proposing that our universe is not the entirety of existence, but rather a four-dimensional brain embedded in a higher dimensional space, often called the bulk. In this framework, the familiar three dimensions of space plus time are confined to our brain, while additional dimensions exist beyond it, largely inaccessible to our perception. Other brains may float alongside ours in the bulk, each potentially hosting its own universe with distinct physical laws, particles, and structures. This idea transforms our understanding of the cosmos. Instead of a single isolated universe, we may inhabit one membrane among potentially countless others, forming a multi-dimensional cosmic landscape whose full scope is impossible to observe directly. The mathematics of brain cosmology emerges from string theory and M theory, where fundamental objects can extend across multiple dimensions. These brains are higher dimensional analogues of membranes, which can exist in various configurations and orientations within the bulk. Our universe could be a three-dimensional surface within a larger dimensional space, with its physical laws arising from the brain's specific structure and position. Gravity is unique in this model because it may partially propagate into the extra dimensions, which could explain why it is significantly weaker than other fundamental forces. This leakage of gravity into the bulk may also contribute to phenomena we observe as dark matter or dark energy, hinting that the dynamics of higher dimensional brains influence the structure and evolution of our universe in subtle but profound ways. One of the most compelling aspects of brain cosmology is its potential to explain the origin of the universe. In some models, the Big Bang is interpreted not as the absolute beginning of space and time, but as a dramatic event arising from the collision or near collision of two brains within the higher dimensional bulk. Such a collision would release enormous energy, generating a hot, dense region that rapidly expands to form a universe like ours. This perspective reimagines the Big Bang as a local event in a broader multidimensional setting, rather than the creation of everything from nothing. Other brains could have experienced similar collisions or none at all, giving rise to universes with drastically different initial conditions or physical laws. In this sense, the birth of our universe becomes part of a larger process occurring in a multidimensional cosmos, where universes emerge, evolve, and perhaps even interact on scales far beyond our observational reach. Brain cosmology also raises the possibility of interactions between universes. While brains are typically separated by vast distances in the extra dimensions, gravitational effects can leak across the bulk. Hypothetical collisions between brains could leave subtle imprints on the cosmic microwave background or trigger large-scale disruptions in matter distribution. These interactions, if they occur, are exceedingly rare and subtle, but they offer a tantalizing link between the observable universe and the higher dimensional reality beyond it. Such a scenario implies that our universe is not fully self-contained. It exists within a dynamic environment where other brains could influence it in ways we might detect indirectly, even if we can never directly visit or communicate with them. The concept of brain cosmology also expands the notion of cosmic plurality. In the bulk, countless brains may exist, each representing a separate universe, some perhaps similar to ours and others radically different. Some brains might have stronger or weaker gravitational forces, different numbers of spatial dimensions, or entirely alien particle interactions. Some could host structures resembling galaxies and stars, while others remain uniform and featureless. The diversity of possible brains mirrors the diversity envisioned in the multiverse and bubble universe scenarios, providing a unified framework that situates our familiar universe as a local manifestation within a vast multidimensional environment. From a philosophical perspective, brain cosmology challenges traditional notions of space, boundaries, and other sides of the universe. If our universe is merely a brain floating in a higher dimensional bulk, the idea of an edge loses meaning. Beyond what we can perceive, other brains may stretch infinitely or form intricate topologies within the bulk. The observable universe becomes a tiny slice of a richer, multi-dimensional structure, bounded not by walls or edges, but by the dimensions we cannot access. Concepts like beyond the universe transform from spatial questions to multi-dimensional ones. What lies beyond might be other brains, higher dimensional spaces, or phenomena entirely alien to our perception. Brain cosmology also intersects with other fundamental cosmological mysteries. It provides a potential explanation for the apparent weakness of gravity, the observed acceleration of cosmic expansion, and the distribution of dark matter. It naturally integrates with the multiverse concept, suggesting that each brain in the bulk could constitute a separate universe, each with its own properties and history. The framework accommodates bubble universes, higher dimensional physics, and variations in fundamental constants, offering a coherent structure in which seemingly disparate ideas converge. By viewing our universe as a brain, we gain a powerful lens for conceptualizing the cosmos as a dynamic, multi-dimensional ensemble, rather than a static, isolated entity. Ultimately, brain cosmology reframes the question of the other side of the universe. Beyond our brain, reality may continue in higher dimensions, populated by countless other brains, each a universe in its own right. The familiar laws of physics, the observable matter, and even the flow of time may be unique to our brain, while the bulk holds realities beyond direct observation. In this view, the universe is not a singular expanse of space and time, but a membrane floating in an incomprehensibly vast, multi-dimensional space, with the potential for interactions, collisions, and a diversity of realities beyond our ken. It is a vision that challenges imagination, extending the frontier of cosmology beyond anything we can currently measure or explore. The dark flow mystery presents one of the most perplexing and intriguing puzzles in modern cosmology. Unlike the predictable motions of galaxies and galaxy clusters influenced by local gravitational forces, dark flow refers to a large-scale, coherent motion of galaxy clusters in a specific direction that seems difficult to explain with known matter and energy distributions in our observable universe. First identified in 2008 through measurements of the cosmic microwave background, CMB, by the Wilkinson Microwave Anisotropy Probe, WMAPI, researchers noticed that certain clusters appeared to be moving at velocities of up to 1,000 kilometers per second toward a seemingly empty region of the sky. The anomaly suggested a gravitational pull from structures beyond the observable universe, implying the existence of matter or forces outside the cosmic horizon that we cannot directly detect. What makes dark flow so compelling is that it challenges the standard cosmological model, which predicts that, on very large scales, the motions of galaxy clusters should be random, driven primarily by local gravitational interactions and the distribution of visible and dark matter within the observable universe. Instead, dark flow exhibits a surprising uniformity and coherence, indicating that something beyond the observable boundary is exerting a gravitational influence. This has led scientists to hypothesize about the existence of enormous, unseen structures or regions of mass lying beyond the cosmic horizon, vast gravitational anomalies that could be shaping the motions of clusters, even though their light will never reach us. In essence, dark flow hints at a hidden universe beyond what we can observe, a realm where matter, energy, or perhaps even exotic physics could exist undetected. Several theories attempt to explain this phenomenon. One proposal is that the dark flow arises from gravitational influences of superclusters or massive structures lying just beyond our observational limit, stretching into regions we cannot see. Another possibility is that the observed motion is a consequence of primordial density variations, remnants from the inflationary epoch that have yet to fully equilibrate on cosmic scales. More speculative explanations suggest that dark flow may be evidence for neighboring universes or higher dimensional structures exerting a gravitational tug on our universe. In the brain cosmology framework, for instance, other brains in the higher dimensional bulk could influence the motion of matter on our brain, creating the observed directional flow. These ideas, while speculative, underscore how dark flow forces cosmologists to consider the possibility that our observable universe is not an isolated system, but part of a larger, more complex structure whose boundaries extend into realms we cannot directly measure. The observational challenges surrounding dark flow are significant. Measuring the motion of distant galaxy clusters relies on detecting subtle distortions in the CMB, known as the kinematic Sunyaev-Zeldovich effect, where photons from the CMB interact with hot gas in moving clusters. These measurements are extraordinarily delicate, susceptible to noise, cosmic variance, and uncertainties in cluster modeling. Subsequent studies have sought to confirm or refute the initial findings, with some showing reduced evidence for dark flow, while others maintain that a coherent motion persists. Regardless of the ultimate resolution, the concept has inspired rigorous scrutiny of the limits of observation and the possibility that cosmic structures exist beyond the reach of even our most sophisticated telescopes. If dark flow is indeed real, it implies that the universe is far more interconnected than previously thought. The motion of clusters toward an unseen attractor suggests that the large-scale structure of the cosmos may extend well beyond the cosmic horizon, with gravitational influences that reach into regions we will never observe. This aligns with broader theoretical concepts like the multiverse, higher dimensional branes, and unreachable regions of space, hinting that the matter and energy shaping our universe may be part of a far grander cosmic tapestry. The mystery also invites philosophical reflection. The universe we see, with all its galaxies, clusters, and cosmic voids, may be just a local sample influenced by vast, unseen structures beyond our capacity to explore. Moreover, dark flow highlights the limitations of human perception and measurement. While light and other signals define the observable universe, gravity may transcend these limits, offering a window into the otherwise inaccessible. In this sense, dark flow is a tantalizing clue that the cosmos extends beyond the reach of our instruments and imagination, pulling us toward questions about the nature of unseen matter, hidden structures, and possibly even other universes exerting influence across otherwise impassable distances. It forces us to acknowledge that the observable universe is just a fraction of what exists, and that the other side of the cosmos may contain phenomena entirely alien to our current understanding. In considering dark flow, we are reminded that the universe may harbor structures, forces, or realms entirely hidden from sight, yet dynamically interacting with the matter we can observe. It underscores the possibility that the cosmos is far larger, more complex, and stranger than what we infer from visible galaxies alone. Even as we map the universe with increasing precision, subtle clues like dark flow hint at layers of reality beyond detection, a cosmic mystery that invites both scientific exploration and philosophical reflection. The flows of galaxies toward unseen attractors may be one of the most direct pieces of evidence that the universe is not bounded by the limits of observation, suggesting that something, perhaps even vast hidden regions or other universes, lies beyond the horizon, silently shaping the cosmos. The concept of parallel realities extends the boundaries of cosmology into the domain of speculation and quantum mechanics, suggesting that the universe we inhabit may not be the only version of reality. Parallel realities, sometimes referred to as parallel universes or alternate dimensions, propose that there exist other branches of existence that diverge from our own universe, each representing different outcomes, histories, or possibilities. While this notion might sound like science fiction, it finds grounding in several rigorous theoretical frameworks, particularly in quantum mechanics and cosmology. According to the many worlds interpretation of quantum mechanics, every possible outcome of a quantum event occurs in its own separate universe. In this sense, an infinite number of parallel realities could exist, continuously branching from each decision, measurement, or quantum fluctuation, creating a vast and incomprehensible multiverse of alternate histories and futures. Beyond quantum mechanics, cosmological considerations suggest that parallel realities may exist in regions beyond our cosmic horizon, where variations in physical conditions, initial parameters, or cosmic evolution produce universes that are, in some ways, alternate versions of our own. In these realms, stars, galaxies, and even life may exist under slightly different physical laws, constants, or spatial configurations. Some universes may be nearly identical to ours, differing only in small details, such as the outcome of a single historical event or the arrangement of molecules on a planet. Others could be radically alien, with forms of matter, energy, and life completely unlike anything conceivable in our universe. The notion of parallel realities challenges our perception of uniqueness. The cosmos may be a vast tapestry of overlapping possibilities, each reality existing independently, yet potentially connected through underlying principles of physics and cosmology. The idea of parallel realities also resonates with theories like brain cosmology and the multiverse. In brain models, our universe is a four-dimensional membrane embedded in a higher dimensional bulk, potentially with other brains floating nearby. Each brain could host its own universe with its own laws of physics, representing a form of parallel reality, causally disconnected from ours. Similarly, the multiverse implied by cosmic inflation suggests that countless regions of space, beyond our observable horizon, could evolve independently, forming universes that constitute parallel realities in a broader cosmological sense. These realities, while inaccessible to direct observation, may share fundamental physical origins with our universe, reflecting different outcomes of inflationary processes or variations in the underlying vacuum state. From a quantum perspective, parallel realities challenge the classical notion of a single, deterministic history. Each time a quantum measurement occurs, multiple potential outcomes exist simultaneously, with each outcome realized in a different branch of reality. This implies that somewhere, in an unfathomably vast multiverse, other versions of ourselves experience every alternative possibility, every choice made differently, every event unfolding along a separate path. While these realities are not physically accessible from our own universe, they exist as genuine manifestations of quantum probability, coexisting in a superposition of multiversal states. In this framework, the universe we perceive is merely one thread in an infinite network of alternate realities, with our cosmic horizon marking the limit of what we can detect or influence. Parallel realities also raise profound philosophical questions about identity, causality, and existence. If every possibility is realized somewhere in the multiverse, then the concept of a singular, unique reality becomes an illusion. Our personal history, the evolution of our universe, and even the constants of nature might be local phenomena, not universally fixed truths. This perspective reframes fundamental questions. What does it mean to exist in a universe if countless parallel versions of ourselves inhabit other realities? Are the laws of physics we observe a local convenience, or do they reflect deeper principles that govern the branching structure of parallel realities? These questions challenge both science and philosophy, pushing the boundaries of what we can conceptualize about the cosmos. The existence of parallel realities also intersects with cosmological observations, albeit indirectly. While we cannot directly observe other realities, certain phenomena, like quantum entanglement, dark energy, or anomalies in cosmic background radiation, could hint at the presence of underlying structures or influences consistent with a multiversal framework. Some theoretical models suggest that subtle interactions between parallel realities might leave traces in our universe, though detecting such effects is extraordinarily challenging. Even so, the concept provides a compelling framework for thinking about the cosmos. Beyond our observable horizon, alternate versions of reality may exist, shaped by different conditions, histories, or physical laws, yet emerging from the same fundamental principles. Parallel realities, therefore, expand our understanding of the other side of the universe. What lies beyond our cosmic boundary may not be empty space, but a vast collection of universes, each representing a different branch of reality. Some may resemble ours closely, while others are entirely alien, governed by different physical constants, cosmological histories, or even dimensional structures. These alternate realities illustrate that the universe is not a singular entity, but a multidimensional, probabilistic expanse where all possibilities are realized. They challenge our notions of uniqueness, causality, and observation, revealing that the cosmos may be far richer and more complex than our senses or instruments can perceive. The concept of the quantum multiverse takes the idea of parallel realities to its most fundamental level, grounding it directly in the principles of quantum mechanics. In quantum theory, particles do not have definite properties until they are measured. Instead, they exist in a superposition of all possible states. The many worlds interpretation, MWI, of quantum mechanics, proposed by Hugh Everett in 1957, suggests that every possible outcome of a quantum event is realized in its own separate universe. In other words, whenever a particle's wave function collapses in one reality, it continues to exist in other realities where each alternative outcome also occurs. Applied on a cosmic scale, this implies an unimaginably vast network of universes, collectively forming a quantum multiverse in which every possible event unfolds somewhere. In this framework, the universe we perceive is only one branch of a branching tree of quantum outcomes. For every quantum decision, whether an electron spins clockwise or counterclockwise, a radioactive atom decays or remains intact, or a photon travels along one path or another, there exists a separate universe in which the alternative occurs. While these other universes are causally disconnected and cannot communicate with ours, they are equally real in the context of the quantum multiverse. The result is a staggering proliferation of realities, each one a reflection of all possible histories and future outcomes. Our own experiences, choices, and observations are just a single thread in this infinite tapestry of existence. The implications of the quantum multiverse extend beyond the microscopic scale to the macroscopic cosmos. Large-scale events, such as the formation of galaxies, the evolution of stars, or even the emergence of life on planets, can be influenced by quantum fluctuations. In some branches, planets like Earth may never form, while in others, life could develop under entirely different conditions. The quantum multiverse thus provides a mechanism for generating a nearly limitless variety of universes, some nearly identical to ours, and others radically alien. Even improbable events, no matter how unlikely, are realized somewhere in this ensemble of realities, suggesting that the cosmos is far more diverse and complex than any single universe could represent. One of the most intriguing aspects of the quantum multiverse is its potential to resolve long-standing puzzles in physics and cosmology. For example, the fine-tuning problem, which questions why the constants of nature in our universe are so precisely calibrated to allow the existence of stars, planets, and life, can be reframed. In a quantum multiverse, where all possible outcomes are realized, it is statistically inevitable that some universes will possess the precise conditions necessary for complexity and consciousness. Observers naturally find themselves in those universes where life is possible, explaining why our universe seems so finely tuned without invoking extraordinary design. In this way, the quantum multiverse provides both a theoretical explanation for cosmic fine-tuning and a broader context for understanding our place within reality. The quantum multiverse also intersects with other multiverse concepts, including bubble universes and higher dimensional branes. Each bubble universe generated by cosmic inflation could itself host a quantum multiverse, branching into countless realities determined by quantum events. Similarly, brane cosmology posits that our universe exists on a four-dimensional membrane within a higher dimensional bulk. Within that brane, every quantum possibility could unfold, generating a further layer of parallel realities. In this sense, the quantum multiverse is not mutually exclusive with other forms of multiverse. It is a complementary mechanism that amplifies the richness and diversity of existence, extending the concept of parallel realities into the fundamental laws of physics. Philosophically, the quantum multiverse forces a reconsideration of notions like causality, identity, and determinism. If every quantum outcome occurs somewhere, then there is no singular, definitive history. Instead, reality is a web of branching possibilities. Every choice, every chance event, and every measurement generates new universes in which alternative outcomes unfold. This challenges our understanding of free will, the uniqueness of our experiences, and the very nature of existence itself. Each of us may have countless quantum counterparts, living out scenarios that differ in subtle or dramatic ways, spread across an infinite landscape of universes. The quantum multiverse thus paints a picture of reality as both deeply interconnected and radically fragmented. A cosmos in which every conceivable possibility is realized somewhere. From a scientific perspective, the quantum multiverse is difficult, if not impossible, to test directly because the different branches are causally disconnected. Unlike galaxies or cosmic microwave background radiation, which we can observe and measure, alternate quantum branches do not interact with our universe in any detectable way. However, the theory is compelling because it arises naturally from the mathematics of quantum mechanics and offers a coherent framework for understanding phenomena that otherwise seem inexplicable. By taking the wave function seriously and considering all possibilities as real, the quantum multiverse provides a lens through which the vast, unseen realms of reality can be conceptualized, even if empirical confirmation remains beyond reach. The quantum multiverse ultimately redefines the idea of what lies beyond the universe. Beyond our observable cosmos, and even beyond other bubble universes or branes, exists a staggering landscape of realities in which every possible outcome of every event unfolds. These universes are not merely theoretical curiosities. They are logical consequences of the quantum structure of reality itself. In this sense, the other side of the universe is not just distant space or hidden galaxies. It is a vast, branching network of universes, each reflecting different possibilities, histories, and futures. It is a cosmos in which the boundaries of reality extend infinitely, limited only by the scope of what is physically possible under the rules of quantum mechanics. The concept of the other side of the universe immediately confronts a profound philosophical dilemma. If the universe has no edge, if space is infinite or unbounded, does it even make sense to ask what lies beyond? Our everyday experience teaches us that objects have boundaries, that one place can be beyond another, and that moving far enough in a given direction will eventually bring us to an edge. But the universe may not conform to these intuitions. In many cosmological models, space is either infinite, extending endlessly in every direction, or finite but unbounded, curved in such a way that traveling far enough in a straight line could, in principle, bring one back to the starting point, much like circumnavigating the Earth. If these models are accurate, then asking what lies beyond the universe is analogous to asking what lies north of the North Pole. It is a question that is meaningful in our everyday experience, but loses coherence when applied to the cosmos itself. Philosophically, the question of the other side challenges the very notion of boundaries. In classical thinking, boundaries define what is inside and what is outside, what is accessible and what is beyond reach. Yet if the universe is unbounded, every point is simultaneously part of the whole, with no exterior space to move into. Even the concepts of direction and distance may become locally defined rather than globally absolute. The universe would not be an object situated inside a larger container, but the container itself, a self-contained expanse in which the idea of beyond is illusory. This forces a re-evaluation of how humans conceive of space, location, and extension, suggesting that some intuitive questions may not have objective answers, only conceptual frameworks that approximate the reality we can observe. The philosophical implications extend to cosmology and physics as well. Asking what is beyond the universe may be akin to asking about conditions outside a system that, by definition, contains all that exists. If space, time, matter, and energy are properties of the universe itself, then the universe is not embedded in a pre-existing void. Rather, the universe constitutes all there is. In this sense, the pursuit of a literal other side may reflect a limitation of human cognition. We are conditioned to think in terms of containers and boundaries, even though these concepts may not apply on a cosmic scale. The universe may be a complete, self-sufficient entity, rendering the notion of an external realm meaningless. Some philosophers and theoretical physicists propose that the idea of the other side may still have metaphorical or functional value, even if it lacks a literal spatial meaning. Considering what could lie beyond forces us to examine the limits of observation, the nature of infinity, and the assumptions embedded in our models of reality. It encourages speculation about multiverses, higher dimensions, and regions beyond the cosmic horizon, serving as a conceptual tool to explore possibilities that may never be empirically verified. In this sense, the question is not merely about physical space, but about epistemology, the limits of what humans can know, measure, or imagine. Moreover, the philosophical lens highlights the interplay between perception and reality. Human cognition and language are structured around relative positions, sequences, and boundaries. But these structures may fail when applied to the universe as a whole. The universe might be boundless, continuous, and self-contained, yet our minds instinctively seek edges, contrasts, and separations. Asking about the other side reflects a tension between human intuition and the abstract, counterintuitive truths suggested by modern cosmology. It underscores the humility required in confronting a reality that may be fundamentally different from what our senses, reasoning, or mathematics can fully capture. From a metaphysical perspective, questioning the existence of an other side also touches on the nature of existence itself. If the universe is truly all-encompassing, then everything that can exist must exist within it, and the notion of an exterior region becomes redundant. This implies that the ultimate unknown may not be a distant place beyond the universe, but rather the limits of knowledge, imagination, and comprehension. In other words, the mystery lies not in what is beyond the universe, but in our inability to conceive of an infinite, unbounded reality in its entirety. The universe, in this light, is simultaneously everything and everywhere, leaving no space for an outside, no place for a literal other side. Philosophically, this also reframes human curiosity. Seeking the other side becomes less about a physical destination and more about expanding the horizons of understanding, exploring the principles, structures, and phenomena that govern existence within the universe. It prompts questions about the nature of space, time, and causality, about the limits of perception, and about the potential for realities beyond our cognitive grasp. Even if a literal other side does not exist, contemplating it illuminates the vastness of the cosmos and the depth of human curiosity, highlighting both our limitations and our capacity for imaginative reasoning. The philosophical lens connects with all prior discussions: unreachable regions, parallel realities, quantum multiverses, and higher dimensions, by emphasizing the relativity of perspective. What we perceive as the boundary of the universe is defined by our observational limits. What we consider beyond may be inaccessible or meaningless, depending on the geometry and nature of space-time. Philosophy thus becomes an essential tool for grappling with cosmic questions that lie at or beyond the limits of empirical science, reminding us that the universe is not only a physical reality, but also a conceptual one, where meaning, edge, and boundary are as much about human cognition as about cosmic structure. Even as we probe the universe with ever more sophisticated telescopes, particle detectors, and theoretical frameworks, the limits of human perception loom as a fundamental barrier to truly understanding what lies beyond the observable cosmos. The universe, as we can see, is constrained by the speed of light and the age of the universe. We can only observe events whose light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. This means that beyond a certain radius, known as the cosmic horizon, events are forever inaccessible to observation. No matter how advanced our technology becomes, no signal, photon, or particle originating beyond this horizon can reach us, making these regions not just difficult, but intrinsically unobservable. This limitation is not technical. It is a fundamental feature of the structure of space-time and the laws of physics. The universe beyond what we can see may be teeming with galaxies, stars, and phenomena entirely alien to us, yet it remains irretrievably hidden, existing as a reality we can infer but never directly witness. Perception limits extend beyond mere distance to the very nature of measurement. Even within the observable universe, phenomena such as dark matter, dark energy, and gravitational waves challenge our senses and instruments. We do not directly perceive dark matter. We only infer its presence from its gravitational effects. Dark energy is known only through the accelerated expansion of space it drives. If these components dominate our universe, accounting for roughly 95% of all energy and matter, then the vast majority of reality operates on levels fundamentally inaccessible to direct human perception. Extending this idea to the unobservable universe implies that even if light or particles could reach us from beyond the cosmic horizon, the phenomena there might be governed by physics that we cannot measure or conceptualize, such as regions with different constants of nature, alternate laws of physics, or higher dimensional interactions that elude all classical detection methods. Our instruments, designed within the framework of our local universe, may be intrinsically incapable of comprehending realities outside these parameters. The limitations of human cognition compound these observational boundaries. Our brains evolved to navigate a three-dimensional world over daily and human-scale distances. Even with advanced mathematics and abstract reasoning, it is difficult to genuinely conceptualize an infinite universe, higher dimensions, or regions entirely disconnected from causal influence. The human mind struggles with the scale, topology, and complexity implied by modern cosmology. For instance, curved or unbounded space defies intuition. A traveler moving in a straight line could eventually return to the starting point without encountering an edge. Infinite universes are equally paradoxical, stretching beyond comprehension and making the notion of outside or beyond meaningless. Quantum multiverses exacerbate the challenge. Imagining a landscape in which every possible outcome of every event is realized somewhere in existence overwhelms intuition and defies standard notions of identity, causality, and probability. Even the most sophisticated mental models are, at best, approximations, offering glimpses into a reality that may forever exceed our capacity for full understanding. Scientific frameworks attempt to push the boundaries of perception, using mathematics as a bridge to the unobservable. Physics allows us to infer the existence of unreachable regions, predict the behavior of unseen structures, and postulate the existence of phenomena like other universes or higher dimensions. Yet these inferences remain fundamentally constrained. Observations rely on indirect signals, often subtle and prone to uncertainty. Mathematical consistency provides guidance, but it cannot guarantee that models correspond to reality beyond the observable universe. As such, the limits of measurement and theory converge. The cosmos beyond the horizon may obey rules, structures, or constants completely alien to our expectations, and even if it is mathematically conceivable, it may be entirely inaccessible to empirical validation. This underscores a profound epistemological boundary. There may exist aspects of reality that are permanently beyond human observation and understanding, no matter how advanced our instruments or reasoning become. The concept of perception limits also connects intimately with philosophical reflections on existence and knowledge. Human inquiry assumes that for a question to be meaningful, it must be, in principle, answerable. Yet when applied to the farthest reaches of the universe, this assumption falters. Asking what lies beyond the cosmic horizon is not necessarily meaningless, but it confronts us with the possibility that the answer may be forever out of reach. The limitations of observation mean that there could be entire realms, structures, or universes whose properties are inaccessible not just practically, but in principle, dictated by the laws of space-time and causality. This suggests that the ultimate frontier of exploration may not be technical or energetic, but conceptual, requiring humans to grapple with phenomena that may never be directly known or visualized. The universe could contain truths that are real, objective, and yet inherently unknowable. Even the indirect evidence we can gather is constrained by perception limits. Consider the phenomena of dark flow, cosmic microwave background anomalies, or gravitational influences of structures beyond the horizon. These provide tantalizing hints of regions beyond our direct observation, yet they reveal only shadows, not substance. They demonstrate that our understanding of reality is always partial, filtered through the limitations of light, causality, and human perception. We can infer the existence of structures outside our reach, but the nature, scale, and dynamics of these structures remain profoundly uncertain. The cosmos beyond the observable horizon may be unimaginably vast, heterogeneous, or governed by entirely different laws, yet it remains largely hypothetical, a domain accessible only through speculation, theory, and indirect inference. Perception limits are also amplified when considering multidimensional and quantum cosmological frameworks. In higher dimensional models, entire spatial directions exist beyond the familiar three, but we are effectively blind to them, constrained to perceive projections of phenomena into our limited four-dimensional brain. In quantum multiverse theories, entire realities branch from every possible outcome, but these branches are causally disconnected. No information from these alternate quantum histories can reach us. Even if these realities exist, our perception and measurement apparatus are confined to the branch in which we reside. Thus, the universe may be a boundless, intricate structure whose richness is fundamentally inaccessible to beings constrained by specific physical laws, sensory modalities, and cognitive architecture. The limitations of human imagination mirror these observational boundaries. While mathematics and theory allow the extrapolation of ideas like infinite universes, bubble cosmologies, or higher dimensional brains, truly internalizing these concepts is extraordinarily difficult. Infinite or unbounded space cannot be visualized in a conventional sense. Higher dimensions cannot be directly conceptualized beyond analogy or projection. The scale of the quantum multiverse overwhelms even the most expansive forms of thought, suggesting that our intellectual frameworks may be inherently inadequate for comprehending the totality of existence. We can describe, model, and hypothesize, but full understanding may be forever beyond reach, highlighting a humbling boundary on cognition. The universe may contain realities that are fundamentally, eternally outside the scope of human experience. Ultimately, Perception limits suggest that the cosmos beyond the observable universe is a domain of profound mystery. It may contain structures, laws, dimensions, and histories entirely alien to our comprehension. Our knowledge is inevitably filtered through the constraints of light-speed communication, causal structure, measurement capabilities, and cognitive architecture. What lies beyond may be forever inaccessible, not only in practice but in principle, rendering the outer reaches of existence permanently hidden. This recognition reframes cosmic exploration. The ultimate frontier may not be a distant galaxy or another universe, but the recognition that some aspects of reality are inherently beyond our grasp, a humbling reminder of the limits of observation, measurement, and imagination. The perception limits of the universe underscore a central theme of cosmology. The cosmos is vast, complex, and in many ways fundamentally unknowable. Every galaxy we see, every cosmic microwave background signal we analyze, and every model we construct is only a local glimpse into a far greater reality. Beyond our instruments, beyond our theories, and beyond our imagination, there may exist entire regions of space, alternate universes, and dimensions whose properties are forever inaccessible. These limits invite both awe and humility, highlighting that the universe is not just a physical entity, but a conceptual challenge, stretching the boundaries of human understanding and imagination to their utmost limits. Even after centuries of astronomical observation, mathematical modeling, and theoretical physics, the ultimate nature of the cosmos remains profoundly mysterious. Among the deepest questions is what lies beyond the universe, or more precisely, whether such a question even has a meaningful answer. All our empirical knowledge is confined to the observable universe, a sphere extending roughly 46.5 billion light-years in every direction. Beyond that lies a domain that may forever escape measurement, detection, and observation, a frontier that is not merely unexplored, but potentially inherently unknowable. The very structure of space-time, coupled with the speed limit imposed by light and the accelerated expansion of the universe, establishes fundamental barriers to discovery. Unlike terrestrial frontiers, where exploration gradually reveals hidden territory, the cosmic unknown might represent a horizon that no instrument, probe, or theory can ever cross. It is not simply the absence of information. It is a boundary dictated by the fundamental laws of physics, placing the universe's ultimate reaches outside the scope of human inquiry. This unknowability does not just challenge our instruments, it challenges the foundations of knowledge itself. Philosophers and cosmologists alike grapple with the implications. If certain regions of reality are permanently beyond detection, then they exist as empirical enigmas, concepts that may be real yet are forever removed from verification. For example, regions pushed beyond our cosmic horizon by rapid inflation, or the relentless acceleration driven by dark energy, are effectively sealed off from causal interaction. No signal from these regions can ever reach us, and therefore their properties, galaxies, stars, physical laws, or even matter itself, are unknowable. We may construct mathematical models or hypothesize about their characteristics, but ultimately they remain in the realm of speculation, forever inaccessible to observation. In this sense, the ultimate unknown is a boundary not of space, but of knowledge itself, where even the most sophisticated scientific methods may fail to yield answers. One of the most intriguing aspects of the ultimate unknown is its relationship to the concept of infinity. If the universe is indeed infinite, as some cosmological models suggest, then the ultimate unknown is not simply a distant region. It is an unending expanse, a realm without edges, repeating patterns, or boundaries in which every conceivable arrangement of matter and energy could occur. Infinity, however, is not just a quantitative challenge, but a qualitative one. It defies human intuition, making it almost impossible to conceptualize what lies beyond a region that is itself beyond perception. Even when cosmologists model the unobservable universe mathematically, they must rely on assumptions and extrapolations that may not hold in these inaccessible realms. The unknowable nature of the cosmos is therefore intertwined with the very structure of reality, challenging both the limits of science and the imagination. The ultimate unknown also intersects with theories of multiverses, higher dimensions, and quantum branching. If parallel universes or bubble universes exist beyond our own, they may lie completely outside the causal reach of our universe, their physics and constants entirely independent of ours. In a quantum multiverse, every possible outcome of every event exists somewhere, yet the branches of reality beyond our branch are unobservable, forever beyond empirical validation. Higher dimensional brain theories suggest that our four-dimensional universe is embedded in a higher dimensional space, with other brains potentially hosting separate universes that exert no observable influence on us. In all these frameworks, there is a domain of existence whose properties are permanently shielded from human measurement, a cosmic ultimate unknown that underscores the limitations of knowledge, observation, and even conceptual comprehension. Yet despite, or perhaps because of, its unknowability, the ultimate unknown holds immense scientific and philosophical value. It drives curiosity, inspires new theoretical frameworks, and challenges our understanding of reality. By acknowledging the existence of regions that cannot be observed or measured, scientists refine their models to account for both the observable universe and the constraints imposed by fundamental physics. Philosophically, it invites humility, reminding us that human understanding is necessarily partial, provisional, and limited by the nature of our observation and cognition. Even as technology advances and theories evolve, some aspects of the cosmos may always remain beyond our grasp, a profound mystery that compels us to reconcile what we can know with what may be forever hidden. The unknowable nature of what lies beyond the universe also reframes the question of human significance in the cosmos. In a universe where vast regions, alternate realities, or infinite expanses exist beyond our observation, our local cosmic environment, our galaxy, our planet, and our species occupies a tiny, almost incidental corner of reality. Yet this recognition is not necessarily disheartening. Rather, it emphasizes the rarity and uniqueness of consciousness capable of observing, measuring, and contemplating the cosmos at all. The ultimate unknown is therefore not only a challenge, but an invitation. It is a reminder of the grandeur of the universe and the depth of questions that can emerge when knowledge encounters its limits. Contemplating the ultimate unknown reinforces a recurring theme throughout cosmology: that the greatest mysteries are not always about distance, scale, or technical measurement, but about the boundaries of comprehension itself. Beyond the universe may lie regions that are physically real, yet epistemologically inaccessible, realms where different laws, structures, or dimensions exist but cannot interact with us, and possibilities that unfold eternally beyond perception. Science, mathematics, and philosophy can provide glimpses, approximations, and conceptual frameworks, but there may always remain an aspect of reality that is fundamentally unknowable. This unknowability transforms the question of what lies beyond the universe into one of the deepest mysteries of human inquiry. It is not just about discovering new places or phenomena, but about grappling with the ultimate limits of existence, observation, and understanding. As we reach the end of this cosmic exploration, it is tempting to focus exclusively on what might lie beyond the universe: the unreachable galaxies, the parallel realities, the higher dimensions, and the quantum branches that stretch into infinity. Yet, after considering the immensity, the unobservable expanses, and the potentially unknowable regions of existence, a more profound question emerges. Perhaps the greatest mystery is not about what exists beyond the universe, but why we exist inside this one. For all the multiverses, all the quantum possibilities, and all the regions hidden from our perception, our universe remains the one where conscious life has arisen, the one in which we can observe, measure, and contemplate. Amid the vast unknown, it is here that awareness, inquiry, and curiosity take root. This shift in perspective invites us to appreciate not just the cosmos as a collection of matter and energy, but as a stage upon which the very act of observation, reflection, and existence itself becomes meaningful. In pondering why we exist in this particular universe, we encounter layers of complexity and wonder. From the finely tuned constants of nature that allow atoms to form, to the emergence of galaxies, stars, and planets, to the conditions that permit life and consciousness, every level of reality seems meticulously balanced to allow for observation and reflection. While theories of the multiverse or infinite universes suggest that our existence could be a mere statistical inevitability, the fact remains that among all possible universes, some unimaginably different from ours, this is the one we inhabit, capable of producing conscious beings who can ask questions about infinity, parallel realities, and the ultimate unknown. There is a profound sense of serendipity in this. Even if other universes exist, we are here, able to reflect on the cosmos and our place within it. This focus on our own universe also highlights the remarkable limits and powers of human perception. Despite being confined to a minuscule fraction of the observable cosmos and entirely excluded from regions beyond the cosmic horizon, we have developed tools, mathematics, and imagination that allow us to conceptualize realities far beyond our immediate experience. We can infer the existence of distant galaxies, speculate about parallel worlds, and propose higher dimensional structures, all from our tiny vantage point within a single universe. In this sense, the mystery of why we exist in this universe is intertwined with the mystery of consciousness itself, why the laws of physics and the structure of reality have produced beings capable not only of surviving, but of comprehending, questioning, and marveling at the cosmos. Our universe becomes not just a collection of matter, but a crucible for awareness, understanding, and meaning. Even more compelling is the realization that the universe we inhabit is a cosmic laboratory of existence. The same laws that govern stars and galaxies also govern chemistry, biology, and life. In a universe with slightly different constants, life as we know it may have been impossible. Within this context, the question of why we exist here is more than a philosophical curiosity. It becomes a reflection on the extraordinary precision and interconnectedness of cosmic structures. The universe is not merely a backdrop for existence. It is the environment that makes existence itself possible. And while science can analyze, model, and simulate these conditions, the fact of our presence remains a deep mystery, reminding us that human experience is not simply a byproduct of physics, but a rare, emergent phenomenon capable of recognizing the vastness and complexity around it. This closing reflection also invites a meditation on significance and humility. When we consider the unobservable regions of the universe, the quantum multiverse, or higher dimensional possibilities, it is easy to feel insignificant, a tiny speck in a vast, indifferent cosmos. Yet there is a counterbalance to this perspective. Within the infinitude of potential realities, our existence becomes a locus of awareness, a point of observation capable of understanding the cosmos and contemplating its ultimate mysteries. We are not merely passive inhabitants of a vast expanse. we are conscious participants, able to witness, question, and reflect. The very act of pondering what lies beyond or why we exist transforms our universe from a vast, impersonal space into a meaningful arena for curiosity, discovery, and wonder. The act of questioning itself, wondering about the unreachable, the unobservable, the unknowable, underscores the unique position of conscious life in the universe. Across the incomprehensible stretches of space and time, only here, in this universe, do minds capable of inquiry exist. The cosmic unknowns, the multiverses, and the quantum possibilities are vast and often beyond direct comprehension. Yet they frame a context in which existence becomes remarkable, precisely because it can be observed and understood. Perhaps the ultimate mystery, then, is not the boundary of the cosmos, the structure of hidden universes, or the reach of higher dimensions, but the fact that any universe contains beings capable of asking these questions at all. Our capacity to imagine, calculate, and philosophize gives this universe an extraordinary significance, not because it is unique in a multiverse, but because it allows awareness to flourish. Reflecting on why we exist in this universe also leads to profound humility. Despite our achievements in science and cosmology, the cosmos remains largely mysterious, and much of it may be forever beyond our reach. We can glimpse, hypothesize, and explore, but the vastness of reality dwarfs our perception, forcing recognition of our limits. Yet in these limits lies beauty. They remind us that existence is rare, observation is precious, and curiosity is both a product of and a response to the cosmos. Perhaps the most profound mystery of all is the intertwining of these conditions. A universe vast enough to contain infinite possibilities, yet precise enough to allow for life, consciousness, and inquiry. Within this delicate balance, the question of why we exist in this universe becomes both a scientific and philosophical meditation, a testament to the wonder of being. Ultimately, the closing reflection brings us back to a sense of awe. The universe we inhabit, with all its galaxies, quantum mysteries, unobservable regions, and hypothetical multiverses, is the one in which conscious life has arisen. This realization transforms our perspective. It is not only about what lies beyond, which may forever elude measurement, but about the extraordinary fact of our presence here. We are observers, participants, and thinkers in a cosmos capable of fostering awareness, imagination, and inquiry. Perhaps the ultimate answer to the question of what lies beyond is less important than the recognition that we exist inside this universe to ask the question, to explore the mysteries, and to marvel at the infinite possibilities that unfold around us. The true wonder, then, is not the unreachable, but the lived reality of consciousness embedded within the vast, mysterious, and awe-inspiring universe we call home. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.